see how this will turn out. All right. Eyeglasses. All right. Oh, the cool shadow that the camera makes on the paper. Maybe some decorations will help us understand the very, very deep logic mathematics here. All right. So, why do I want to understand quadratic reciprocity? It's because C.F. Gauss, Carl Friedrich Gauss, called this quadratic reciprocity QR as the Aureum theorema. And I honestly still do not understand what the heck is QR. Like honestly, like I've been trying to explore in what ways I can, but it's resistant to my understanding. It's not exactly easy to understand. But let's just let's try to me trying to understand QR on a YouTube stream might be a pretty good exercise. So let me see here. We might need a spreadsheet. Let's see. Couple stuff. Checking. Alright, just checking my screen. Okay. Cool, I can open it up on a web page. Okay. Besides my streaming software. Checking. Alright, just checking. Alright, just checking my screen. Okay. Cool, I can open it up on a web page. Okay. Besides my streaming software. So let's see. When I sort this by view count, as I've already done, it's really Mathologer, who is by far the most popular YouTube video about quadratic reciprocity. QR. Now, every time I hear a QR code, I'm going to think a little about quadratic reciprocity.
Today I'd like to talk about one of, some say, the most amazing formula in the whole of mathematics, the law of quadratic reciprocity, that formula over there. Which proves that mathematicians are crazy, right? I can tell what you're thinking. P over Q times Q over P equals some power of -1, so the fractions cancel out, making the left side equal to 1. But what if, say, P and Q are both 3? Then the right side simplifies to what? Okay. -1. 1 is equal to -1. Does this mean that the most amazing formula is plain wrong? Okay, so you guessed it. Mathematicians may be crazy, but we're not that crazy. So whatever's going on, those aren't everyday fractions on the left side. I leave it as a mystery for now, but of course all will be explained. First, I want to get you
understand this very difficult to understand thing. know if you can even see that. I don't know.
You're really curious with a bit of history and some amazing facts. Then, once you're truly hooked and there's no turning back, we'll go together on a crazy journey. Trust me, this mythology is an extra wild one. The law of quadratic reciprocity was discovered by mathematical hero Adrien-Marie Legendre and the superhero Leonhard Euler. They came upon it while pondering questions like Fermat's two-square theorem, that great theorem which I talked about in my last video and with which so many of you also seem to have fallen in love. And who was the first to prove the theorem? The answer, of course, as is so often the case, was not Euler. Tricked you? Hard to believe, isn't it? But we finally stumbled upon a theorem that vanquished the invincible Leonhard Euler. So who was the first to actually succeed in proving the law of quadratic reciprocity? It was none other than that other mathematical superhero, Carl Friedrich Gauss. It's like a Marvel movie, isn't it? If one superhero is beaten down, another comes to the rescue. Now, throughout his life, Gauss proved the law in 8 different ways. Amazing, isn't it? Clearly, Gauss believed that the law of quadratic reciprocity is incredibly important. In fact, he called it the fundamental theorem of higher arithmetic, or the golden theorem. And Gauss was not alone in his respect for this theorem. There are now over 200 published proofs of the law, lots of them by other mathematical big hitters, Eisenstein, Kummer, Cauchy, Jacobi, Liouville, Lebesgue. 200 is more proofs than just about any other theorem in maths, apart from maybe Pythagoras' theorem. So seemingly an incredibly important theorem. But then how come about 99.99999% of humanity will never have even heard of quadratic reciprocity? Well, let's find out. My first mission today is to motivate and to explain quadratic reciprocity, which will already induct you into a very select group. But my ultimate and completely insane mission in today's video is to take one of those crazily complicated proofs of quadratic reciprocity and to mythologize it to death, to get it within reach of YouTubing maths fans. Luckily, I found a great starting point for this mission, a blog post by mathematician Matt Baker. Matt takes the 1830 proof by the Russian mathematician Egor Ivanovich Zolotarev and interprets Zolotarev's proof in terms of permutations and dealing a deck of cards. Really great stuff to look forward to. Well, I've also put a link to Matt's blog post in the descriptions for all you mathematicians. Okay. I first need to take you on a journey back to some school maths. No, wait, come back. I promise, it will be fun. I'm going to cast some familiar school mathematics in a new light. You all know what a ring is? No, not a Lord of the Rings ring or a wedding ring. You're safe. I'm not about to propose. A maths ring is a world of number-like objects. So these objects can be added, subtracted, and multiplied, maybe in some weird way, but they still obey the same simple algebraic rules that we've all internalized in school, a plus b is b plus a, etc. Not surprisingly, the integers are a ring, and so are the rational numbers and the real numbers and the complex numbers. Are there other rings?
Okay, I actually really want to understand this well. So, rings. I see this so much when I just glance over math stuff. So a plus b, a times b, and the distributive property. So that's the commutative property on the top here. A plus b equals b plus a. You can commute those. A times b equals b times a. You can commute those, just which means commute means you just you commute, switcheroo. It's just the distributive property, a times b plus c equals a times b plus a times c. Okay, so.
Well, as I hinted, you already
Basically,
rules that we've all internalized in school, a plus b is b plus a, etc. Not surprisingly, the integers are a ring, and so are the rational numbers.
Oh, he puts etc. there, so there's a lot of other stuff.
And the real
Etc. is right there.
numbers and the complex numbers. Are there other rings? Well, as I hinted, you already know some other rings from school. They were just never identified as such. There are actually infinitely many of these rings hiding inside the integers. There's one of these rings corresponding to each integer greater than 1. Okay, let's start by having a close look at the ring corresponding to the number 5. In this video, I'll call this ring Z5, which is its official name.
Ring Z5.
This cute mini-ring has only 5 numbers: 0, 1, 2, 3, and 4. These numbers are the possible remainders when you divide integers by 5. To add and multiply these remainders, the numbers in Z5, you add and multiply them as usual, and then calculate the remainder on division by 5. Here are a couple of examples of how arithmetic works in our mini-ring. Let's add 3 and 4 in our mini-ring. So we add 3 and 4 as usual, giving 3 plus 4 is 7, okay. Now the sum in our mini-ring is just the remainder when we divide 7 by 5. And of course this remainder is 2, right? 3 times 3, well, in Kansas, of course, this equals 9. But now, in this particular corner of the magical land of Oz, the product is the remainder after dividing by 5, which gives us, well, 4, of course. Pretty easy, right? Even if you've never heard of modular arithmetic, which is the official name of what we're doing here, I'm sure you could all now fill out the addition and multiplication tables for our mini-ring. There. And the same easy process works for any integer greater than 1. Here are the tables.
Let's see here. Put this in a. And okay. I actually saw this video like a couple weeks ago. Try to do it on my own, and well, what happened was I just got tired. This is a long video. It's 1 hour, and when I just kind of skedaddle along as Mythologer does, it doesn't. I'm not convinced unless I really understand every single piece of this. So I have to really understand it well. I have to really be pretty rigorous. Okay, so basically, say this is easily programmable in spreadsheets. Let's see here. Basically, you just do this. Equals to this. used to LibreOffice's way of doing things. Dollar sign should mean that only that stays constant. Right, let's see here. Okay. A little rusty on my spreadsheet skills, but I guess this is all correct. I might just leave it here. I'm not feeling like doing a marathon tonight. But eventually we will, I hope to eventually understand this well. And maybe these YouTube videos I make will also allow the viewer to understand this well. Does it matter in our lives to understand QR? Maybe it does. Maybe it really does influence some software that we will program one day. Alright, as an exercise, I'm just going to try to get this done as well. It's more spreadsheet skills practice than anything. Alright. QR. Now every time I hear QR code, I'm going to think quadratic reciprocity code. Alright. Should just be pretty simple here for a spreadsheet. Alright, this looks pretty good. Alright, that's all I feel like doing tonight. code this. As if that matters. Alright, he has yellow and green. He's our teacher, so what's the best way to what kind of color scheme do I want here? I want something other than just white. Let's do light purple too. Just do purple. Yay! I'm coloring this like my daughter colors coloring books. Alright. Colors matter. Colors matter. The white is so beige. The white is so beige. But white is all the colors combined. White's all the colors combined. Alright, color coded like Mythologer, because hats off to Mythologer for creating this pretty cool video. By far the most popular YouTube video about QR. I wonder why he didn't color the rest of this yellow. Like it matters. He has the headers of the columns and rows as white, but didn't color them yellow. No, nor does he color. What made him choose yellow and green? Yep, that is the $1 billion, $1 bazillion question. Is Mythologer's color choices. Alright, I'm going to continue this later. I just feel like I don't have enough time to really dive too much deeper. Alright.